In this video, we're going to further examine the law of mass action. We will look at the decomposition reaction of dinitrogen tetroxide at 200 degrees Celsius, N2O4 in the gas phase in equilibrium with 2NO2 in the gas phase. We are also given the initial and equilibrium concentrations of dinitrogen tetroxide and nitrogen dioxide to calculate the equilibrium constant for this reaction. The equilibrium expression of this particular reaction is the ratio of the equilibrium concentration of nitrogen dioxide squared over the equilibrium concentration of dinitrogen tetroxide, regardless of the initial conditions that we begin with at the same temperature. Let's look at some experimental data and find out. In this table, we see 3 experiments with different sets of initial and equilibrium concentrations of dinitrogen tetroxide and nitrogen dioxide. For the first experimental conditions, we began with only the reactant, dinitrogen tetroxide. When the reaction reaches dynamic equilibrium, we should expect some dinitrogen tetroxide molecules to break down into nitrogen dioxide molecules. When we calculate the equilibrium constant for the first experiment, we get 10.4. For the second experimental condition, we began with only the product, nitrogen dioxide. In this case, we should expect some nitrogen dioxide molecules to combine and form dinitrogen tetroxide molecules. We calculate the equilibrium constant for our second experiment. We get 10.4. Finally, for the third experimental condition, we began with an equal amount of reactants and product. In this case, more nitrogen dioxide molecules are produced when it reaches dynamic equilibrium. We will discuss later how to determine the direction of equilibrium moving toward product or reactant. Let's try to calculate the equilibrium constant one more time for the third experiment. Again, we get 10.4. The equilibrium constant is the same for all 3 experiments with different initial conditions. To conclude, different initial concentrations can lead to different equilibrium concentrations, but the ratio of the equilibrium concentrations of products divided by the equilibrium concentrations of reactants, each raised to their own coefficient, remains unchanged at the same temperature.